Back to lesson 13. Sorry about the disjointedness of this lesson. We're going to complete B and then go back to the question that we missed. So in question A, in part A of this example, of example 3, we calculated the velocity when the electron went from the negative plate to the positive plate. So in other words, it converted all its potential energy into kinetic energy. Now, in this next example, we're going to calculate the velocity when it's only moved through 1 centimeter um, of the plates. The plates are 4 centimeters apart, and we want to calculate the velocity when it's only moved 1. And it's a mistake to think that since it's only moved a quarter of the distance, so here's the plates, right, and it's an electron, right, so it's going to be electron. It's a mistake. So here's the electron, and it just goes through 1 centimeter. There's 4 centimeters between the plates, and it's just going to go through 1 centimeter. It's a mistake to think that therefore the velocity is 1/4 of that velocity, right? Because it's accelerating, right? So it's an exponential curve. Therefore, it's not going to be 1/4 of it. So don't think that. Here's how we're going to do that question. So the first thing we're going to have to calculate is what is the electric field strength? It's a uniform electric field. So we can use the information that we have to calculate the field strength of the parallel plates. E equals V over D. We know that the voltage is 20. Is it 20? Yep. And the distance between the plates is 0.04. So that gives us 500 volts per meter. So that's the electric field strength between those two plates. Now, the particle, the electron, has only moved through the 20 volts between the two plates. It's only moved through a quarter of it. So you can, for that one, you can actually say, yes, if it's 20 volts between the two plates, 4 centimeters, then a quarter of 20 is 5. So it's only moved through 5 volts of the potential difference. But let's just do it mathematically just to verify that. So we're going to use the same formula because now we've calculated the electric field strength of the whole thing. And now we can calculate what voltage has it gone through, or what is the potential difference, 500, when it's only gone through 1 centimeter, so 0.01. And of course, 500 times 0.01 is 5.0 volts. So it's only gone through, out of the 20 volts between the plates, it's gone through a quarter of that, which is 5 volts. It's gone through 5 volts of potential difference. And then now that we've done that, then the rest of the question becomes very much like the previous question. In step 3, we're going to calculate we're going to use the voltage formula. The voltage equals the change in energy divided by the charge, and we're going to calculate the change in energy, right? The change in energy from here to here, as it goes through 1 centimeter of potential difference. It's going to equal VQ, which equals 5 times, and we're talking about an electron here, so that's 1.6 times 10 to the negative 19. That gives us 8.0 times 10 to the negative 19 joules. So that's how much energy it's gained. Let's just review to see, does that seem reasonable? In the first example, when it went through the entire 4 centimeters, it gained 3.2 times 10 to the negative 18 joules. This time it's gained 8.0 times 10 to the, that should be a negative 19 joules. That seems pretty reasonable. And then in the fourth step, you can just calculate the velocity using our velocity formula, 2ek over m, square root of 2 times the gain in kinetic energy divided by the mass. It's an electron, so it's 9.11 times 10 to the negative 31, and that's going to give you a velocity of 1.3 times 10 to the 6th meter per second. right? Which, if we did this in exact values, you would find out it is actually a quarter of the answer that you got. Sorry, not a quarter. What am I saying? It's a half. It's a half of this value right here. So in this one, we got 2.7. This one, we get 1.3. And if you didn't round off, you'd find out actually those values are exactly 1/2. So the thinking was that it only went through a quarter. The potential difference for the velocity should be a quarter. But no, that's not true. It's actually a half because, as I said, it's an exponential relationship. Okay, so that's that question. That's one of the harder questions. Now let's go back to the question that we missed, which is example 2. On the previous page, an alpha particle moves through between two parallel plates that are 2.7 times 10 to the negative 2 meters apart, with a potential difference of 130 volts between them. Determine the force acting on the particle. Determine the force. So the first thing we need to do is figure out the electric field strength. We've got an alpha particle, and once again, let's write down everything that we have. As soon as you see alpha particle, then you can say that you have the charge. The charge of an alpha particle is 2.3 times 10 to the negative 19 coulombs. The mass of an alpha particle is 6.65 times 10 to the negative 27 kilograms. Right, we got the distance between the two plates, 2.7 times 10 to the negative 2 meters, and we've got the voltage, 130 volts. Determine the force. We're trying to find the force between them. That's what we don't know. So if we start from here, force equals, what is the electrostatic force equal? We have two formulas for electrostatic force, and the one that we're going to use is EQ, based on this formula here. The electric field strength equals the force divided by Q. If we arrange that for the electrostatic force, then we get this here. So what do we need? We have the charge right there. We need E. We need the electric field strength, and since it gives us D and V, that's pretty easy to calculate. So in step 1, the electric field strength equals the voltage divided by the distance. That is going to give us 130 divided by 2.7 E negative 2, and that gives us an electric field strength of 4,815 newtons per coulomb. And then in step 2, to calculate the force, we can just use this formula here. 3.2 times 10 to the negative 19, and we get an answer of 1.5 times 10 to the negative 15 newtons. And just a common addition to that question would be to then calculate the acceleration. So if I put a part B to this, it would be calculate the acceleration, and we can do that using our old friend. Acceleration equals the force divided by the mass, and so that would be 1.5 times 10 to the negative 15 divided by the mass of an alpha particle. And that is going to give you, where's my calculator? It's going to give you 1.5 divided by, 1.5 E negative 15 divided by 6.65 E negative 27. And once again, you're going to get some huge numbers for these, for the acceleration of particles in electric fields. It turns out to be 2.26 times 10 to the exponent 11 meters per second squared. So that might be an additional question that you would be asked on a question of this nature. Good. That ends lesson 13.